David Sumpter, who's actually a mathematician who gave a talk on our channel a few weeks ago, asks a question about the stability of the rule sets. So if you change them slightly, then you get a completely different output, whereas in biological systems, you can change a gene here or there, and like 99% of the time, it's not going to really have any effect. So would you say that that's a similar thing or a difficulty with it?
Okay, so it's a little bit complicated. It's like there are things that change dramatically, and there are things that don't change at all. It's the same thing that one sees in materials. Like let's take water. I keep on using this analogy. The properties of water as a fluid depend. If you change the properties of a water molecule, you don't change the overall fluid properties of water. And so it is here. The fact that you get general relativity is generic across a large collection of rules. The particular details, well, actually, the things like the mass of the electron, that will change. Probably, we don't know for sure, that will probably change dramatically from one rule to another. In the case of general relativity, the actual Einstein equations seem to be generic. There are corrections to Einstein's equations, which we're currently trying to work out, and those will not be generic. But those haven't been observed yet. But those will be, we think, rule dependent in a way that, just like in the case of the properties of a fluid, the details of the structure of molecules doesn't affect the fact that a fluid satisfies the fluid equations, the Navier-Stokes equations, but things like the viscosity of the fluid are affected by the details of what the underlying molecules are. But it's one of the things that's sort of inevitable when you have a sufficiently simple rule. There will be some dramatic differences going rule to rule. It's not it's not something where you say it's not. Think about it, in the case of neural networks, which are a great example of kind of a thing that's sort of a found feature of the computational universe. You're picking this program. It's a very complicated program. The main sort of discovery of neural networks is that you can make these programs that are big enough that it actually works to have incremental change of the program. And that's something, if the rule for the universe is sort of as big as your average neural net, then yes, you can expect to have sort of some local motion in the space of rules not making much change. If instead the rules are sufficiently simple, then it is inevitably the case that some features will change dramatically from rule to rule. But in terms of the analogy with biology, I think it's kind of interesting because this formalism that we've developed for physics turns out to be applicable to lots of other things too. So just like cellular automata are kind of the ultimate idealization of parallel computation. You've got this grid of points in space and time, and you're updating every point in parallel. These models, based on updating hypergraphs, are kind of generic models that don't rely on the existence of an underlying space and time. And it turns out there are a bunch of things. So the most immediate one is distributed computing, which this turns out to be both a very interesting model for, where you can both import ideas from distributed computing to physics, and probably more interestingly, you can import ideas from physics to difficult problems in distributed computing. And in the future, people will start talking about, I am programming this particular distributed computing system in a particular reference frame. Because that's kind of an importing from physics of ideas that kind of get transported by these models. But they're also a conceivable direction is using these models to understand some things about biological evolution, which has been an area that has had a lot of trouble getting kind of really formalized in an adequate way. And that's too early to say too much about that, but it's kind of interesting that the way these multi-way graphs work, it's just a general kind of formalism that allows one to have a slightly different view. One's looking at a sort of a larger scale. One looking at sort of all possible paths of evolution, so to speak, which is something one hasn't tended to look at in the way that one analyzes kind of evolutionary processes. But that's kind of a separate thing. I think, to say about the stability of biological processes and so on. I'll make the following comments at a different level about biology. So one of the questions of biology is, what is the right paradigm for thinking about it? So if you look at, for example, the history of genetics, pre-1950s, genetics was a big, complicated area where there were just a ton of phenomena. People didn't really know how it fit together. 1953, the encoding of information on DNA was discovered. It became clear that digital information was the key to what was going on in genetics. Today, when we look at biological processes, we look at these giant charts of, metabolic pathways of the cell and things like that. there is a certain paradigm that we think about in terms of, differential equations with the concentration of this and, these proteins interacting with these other ones. But it's not really clear what the correct kind of large-scale paradigm is. It's, how much detail do we have to get into about the precise configuration of these molecules? How much actually matters? Just like when we thought about genetics before 1953, you might have said, well, it really matters what the actual precise curvature of this particular DNA molecule is. Actually, it doesn't matter. All that matters is this digital information that's encoded in the genome. And so one of the things that's an interesting question, I don't know the answer to it, I've thought about it for many years, and although now we have kind of a different formalism to think about it again, is what is the right underlying way to think about kind of the processes of systems biology, so to speak? And how does, what is the right level of description at which we can start discussing, what fundamentally happens in aging? There are certain details we know, but is there a bigger picture to what's going on? And do we have kind of a computational way to understand that bigger picture? And I can't report success, but at least I can report that we have at least a different set of kind of raw material for models for thinking about those kinds of things. But I don't know how that's going to come out yet.
Particularly big thanks to your colleague Jonathan, who's been heroically answering loads and loads of questions as they come up, and he's been absolutely fantastic. I've been trying to learn from him and learn from you at the same time. It's been amazing to hear. So a lot of people in the chat, Stephen, before we go, have been asking sort of where can I find out more, where can I read more books on this, and so wolframphysics.org is the best place to start, I would have thought. Yeah, but is there any other?
There's a book version, but you can find all of this on the web. But
fantastic.
Wolframphysics.org is the right place to start. And we've been, one thing I might mention is that we've been doing this as a very open science project. So we live stream a lot of our internal working sessions. In fact, we have one coming up this afternoon, where we're kind of doing this as open science, and it's been really great to see lots of people participating in it, both professional physicists and others. So maybe we'll see some of you there.
Absolutely fantastic. Well, so I just want to say goodbye to everyone, and we managed to get through the entire event, and we didn't mention the election once, so that was pretty good, I think. So everyone, if I could just say take care to everyone, and thank you so much, Stephen, for an absolutely amazing talk. Thank you so much.
Thanks. Okay, bye-bye.